Okay, so it's week 6. I'm working on writing up homework 3, so you can expect to see that soon, and I'll post that online, and that'll be due sometime next week. I just want to kind of wrap up a little bit. I don't know if wrap up's the right word, but cover a little bit more on some of these ideas in Bayesian statistics. Okay, as they will play a little bit of a role, or they will play a role in some of these future analysis methods that we'll cover. We're going to have to skip some sections and whatnot, but first I thought we'll continue on with kind of just this overview illustration of kind of Bayesian statistics here. Okay, so the premise with Bayesian statistics is that we are treating everything, even the parameters that define our distribution, as random variables. Okay, so we treat pretty much everything as a random variable. Maybe not pretty much everything, but a lot of things as random variables. So even the parameters that define the distribution are considered random variables. Sorry. Okay. And so we were looking at our running example was the coin flip game, right? Okay. And so observations from a coin flip game would follow the binomial distribution. And the binomial distribution has two parameters. N and P. Okay. Or I'm sorry. In our case, we're using the letter R. R would be the probability of success. Now we will treat N as N will be treated as fixed. And therefore, the likelihood of our data, or basically the probability of our data, but we'll call this the likelihood, is the probability of our sequence given some value R. Okay, and this can be thought of as you do your N choose. And choose the number of successes, R to the number of successes times 1 minus R to the N minus our successes. Or we can just use this in R. This is, we have D binom, and we would say, however many successes we have based on the number of flips and the probability R. Okay, and we took a look at this already when we created some likelihood plots. Okay, and when we plot the likelihood, okay, we plot it as a function of r. And so, for example, we can, when you create a plot, you create a sequence, and as far as r goes, the probability of a success, that goes between 0 and 1. And so we can just say, let's plot the likelihood if I see 6 heads out of 10 flips. Okay, and so we can plot that, and if I do this, the likelihood looks like this. Okay. And when we talk about maximum likelihood estimation, we're basically talking about picking the value of r that maximizes this likelihood function. Okay, and so if when we look at this, we can see that the maximum is at 0.6. But if we wanted to, we could run a little optim, the optim command in R to optimize that. How would we do this if I want to do that? So if I want to do maximum likelihood estimation with optim, first I would have to create a function, right? So the function that I'll call this likelihood. This is going to be a function of r, and basically the likelihood is just this. So this is effectively the function that I want to optimize, and I would just say optim. And if we're, the way you run the optim function is you give it the parameter, and in this case we want to optimize the parameter value r, and then we give it the function. We can specify the method, but we can just basically say starting let's start at 0.5, and the function that we want to optimize is the likelihood. Okay. Now again, because I only have, this is a univariate thing, I should specify a method that's something other than Nelder-Mead. So maybe I'll just say BFGS. Okay. Oops. Did I not say that's a function? Okay. Yeah, it says something broke. What am I doing? Lower and upper must be finite values. Oh, okay. Yeah. Lower is 0 and upper is 1 as far as what we go, and then this should work. The parameter. Am I messing something up here? Okay. Oh, I'm sorry. The likelihood, we need to, optim always minimizes, so I just need to do -1 times this. I was getting worried for a second. Okay, so we run this, and then it says the one that maximizes or minimizes the negative of the likelihood, or basically that maximizes the likelihood, is 0.6. Okay, so maximum likelihood with optimization, optim tries to minimize. Okay. Yes?
What if your likelihood function was multivariate? How would it know which variable to optimize over?
It would optimize over all of them. It would optimize over all of them. So, yeah, that it would try to find the combination of parameter value set that would optimize that. So, for example, if I just do r sub 1 and r sub 2, I think it'll try to optimize this, and although I don't know how the let me just get rid of everything else. It's angry here. Okay. I don't know. I'll have to mess around with it some more. But yeah, we can maximize the likelihood. Basically, we're effectively just maximizing the likelihood function here. Okay, let me. Okay, so anyway, that's the likelihood part. Okay, now as far as what we're trying to go for is, what we want is we want the distribution. This is called the posterior distribution of our parameter R based on the data that we observed. Okay, so what we're going for is we want to know what is the distribution of this random variable R, the distribution of the parameter, because in Bayesian statistics we treat our parameters as random variables. And this is going to be equal, using Bayes' rule, it's the probability of our data, or the likelihood of our data, multiplied by the probability of our parameter R, divided by the probability of our data in itself. Okay? And so we've already looked at this first part. This is the likelihood. Okay? Okay. We call this part. This is the prior. Okay? This is the distribution of our parameter R before we've taken a look at the data. The prior distribution, so it's called the prior because it's before we look at the data. The prior distribution represents and we can just say what we believe is the distribution of R before we take a look at the data. Okay? And so basically, if I show you a coin and I say, what do you think the probability of this coin landing heads is? Most of you would say, I think it's 0.5. Okay? And if that's a non-negotiable fact for you, meaning that for you, the prior distribution is that a coin must land heads with probability 0.5, and I will not accept that the coin will land any other probability, heads with any other probability, then your prior distribution will be that is basically a spike that's infinitely tall at the point R is equal to 0.5. Okay? And that means no matter what happens with our data, when we do our multiplication, the ending result here is going to just be, still it's going to be 0.5. Okay? If you say there's no other possibility that the coin will land heads, I will not accept that, then it doesn't matter, right? Data has no meaning to you. You're just going to say, this is what I believe, this is what I'm sticking to. I don't care what you show me, this is what I'm sticking to, okay? And that would be reflected in this thing, PR, okay? So, I believe, coins land heads with probability equal to 0.5, no matter what. And, no amount of evidence can change my mind, okay? And basically, that prior belief is just this. At 0.5, there's a spike at going up to infinity, and everywhere else, it's 0. Okay? And generally, I think, well, a lot of people will say, well, I'll look at the evidence and that will shape kind of what I believe here, okay? And so when we're talking about the carnival game, maybe your prior belief is, oh, you know what, the person running the game, I think is an honest person, so I think he would be using a fair coin. We might, I believe the coin is fair, but evidence can change my mind. So we would put 0.5 here, and probably our prior belief. This looks terrible, but our prior belief looks probably something like this. Okay, to reflect this. So we would say, it is possible that the coin is something other than 0.5. This represents our prior beliefs about the distribution of the coin. About the distribution of R. Okay, R being the probability that the coin lands heads. We think there's a pretty good chance that R is 0.5, and we go with that, right? So, if I were to just flip a coin and the coin lands heads, 54 times out of 100, okay, we're not immediately going to say, okay, now I believe coins lands heads with probability 0.54, because our prior beliefs are very strong that the coin lands heads with probability 0.5, and that's what we go, okay? On the other hand, if we say something like, I believe, the coin might be biased to land heads more often, we could have something that looks like this. Okay. Oops. This is a possibility. Another possibility is, maybe you think it's, or between 0 and 1 as far as the distribution of R goes, maybe you think it's something like this, okay? And you suspect it's around 0.8 or whatever it might be, okay? So the prior represents our belief about the distribution of R, or whatever parameter we're talking about, before looking at the data. Okay. And we can just draw these. There are some, as far as priors go, for the binomial, we have there's the beta distribution. Are you guys familiar with the beta distribution? Sorta? Okay. All right, so the beta distribution it can represent our prior beliefs about the coin. Okay, the beta only goes from 0 to 1, okay? Beta will have non-zero values only between 0 and 1. And there's all these funny symbols. The exact formula for the beta distribution I don't think is as critical as just this idea that it represents our prior beliefs about the coin, and it's defined by two shape parameters, okay? Sometimes they are alpha and beta, other times they are delta and gamma and delta. We use two letters to represent the shape parameters for beta. Okay, and basically the beta distribution can look like this. Okay, if alpha is equal to 1 and beta is equal to 1, then the distribution looks like this. Okay, basically meaning that any value of r is possible. Any value of r is equally likely, or equally likely. This is what we would call a, quote, non-informative prior. This is about as open mind as you can have regarding the coin. You're saying, before I look at the coin, before I look at any data from the coin, I'm going to say I have no idea. The coin can land heads anywhere with probability between 0 and 1, and they're all equally likely. Okay? As soon as you start changing these values of alpha and beta, then it changes the shape of the distribution. Okay, and what you can kind of think of it is this is a very loose idea here. Okay, that don't actually mathematically this is not necessarily how it goes, but the loose idea is that alpha can represent the number of times you saw heads or a success, okay, prior to your current data. Okay, alpha could be quote, number of heads observed prior, and beta could be number of tails observed prior. Okay, and so what that means is if alpha is equal to 50 and beta is equal to 50, then this promotes the idea that we have a distribution where we are centered at 0.5. Okay? And on the other hand, if we have alpha equal to, say, 5 and beta equal to 1, then this would suggest a distribution that favors one side over the other. Okay, and everything in between. There's a nice algebraic property of the beta distribution and the binomial distribution working together, and so we say that the beta is the conjugate prior for the binomial. Okay, so the beta is the conjugate prior for the binomial. Okay, and I guess maybe I'll have to define that a little bit more clearly. It just means that when you use the beta distribution as the prior and you do the multiplication here, okay, because so if I can flip back a slide, because if this part follows the beta and this part follows the binomial, okay, and when you multiply these two together, if you have a conjugate prior working with the probability distribution, there's some nice algebraic properties on how they multiply together. Okay, otherwise you're just multiplying two different probability distributions, and it could get messy. All right, the conjugate prior just says when you multiply that thing with this thing, it works out nicely. Okay, that's all we're saying. Okay, so the conjugate prior just says, yeah, this might be the preferred one that we have. Okay, so let me just kind of show you, illustrate how this works a little bit. Okay, so let me just show you. Here's some different beta distributions, and maybe I'll make another one. These are the ones given in the textbook. But you know, if I say 5 and 5, okay, so prior A will be having, what is going on? Okay, so let me just So this right here, this represents the beta distribution if I'm using the shape parameters 50, 50, okay? Meaning that we're expecting the probability of it landing heads to be around 0.5. The R value we expect to be around 0.5. If it's 1 and 1, then it's flat, okay? And let me also just show, if I only do 5 and 5, what do you think this line would look like? So I'll do a red line where the shape parameters are 5 and 5. So it's kind of the idea that so far we've only seen 5 heads and 5 tails, sort of. Okay? And so when I plot this, it's still centered at 0.5, but we're going to allow for a lot more kind of variability in our predictions here. Okay? And if I say, you know, I've seen like 25 heads and 4 tails, okay, and I plot this. Let me do, we'll do green here. Okay, this indicates kind of where we our beliefs about the location of R. Okay, indicating that after seeing 25 heads and 4 tails, this is kind of what we believe. So the prior combines those two together. Okay. Let me flip back here. Okay. So the probability of the posterior distribution of our parameter R after we've seen the data Y is the likelihood of our data multiplied by our prior information. Okay. And then we divide that by probability of Y of the data itself. Okay. This is called the marginal. This piece over here, this is known as the marginal. What's important to note is that the marginal distribution does not depend on R itself. So as far as R goes, this is just a constant. Okay, constant as this piece does not depend on R. Okay, and the truth is that as far as this marginal quantity goes, it is generally very difficult to calculate. So let me just write a couple notes about that in our few last moments. The probability of Y sub n, this is known as the marginal distribution. Marginal distribution of our data Y. Okay? And this basically is the total probability of getting this exact data across all possibilities of our value R. Okay? That's the idea here. It's the total probability of observing our data Y Y sub n across all possible values of our parameters. Okay, so formally, if you want the math for it, it would be the equation for the binomial would be from 0 to 1 of our data. So this is our data given our parameter value across every single possible parameter value. This is it's a constant, okay? That doesn't depend on R. So what that means is that our posterior distribution, the posterior distribution, we can say is some constant multiple of, here, well let me first do the equals. The posterior distribution is exactly equal to this, but because this is a constant, we can say it is similar to just the numerator. Only the numerator is the part that really matters. Okay, and if we just say, well, there's some value here that we multiply so that the total area is equal to 1, then that's it, okay? But if we don't worry about this, then we're going to have some kind of shape here where the, you know, the area under the curve is not necessarily equal to 1, but it's still, like, we can use that shape to figure out where the maximum is. We can use that shape to figure out, you know, a lot of answers without actually getting the thing. So, so if I wanted to get the shape, I can take our likelihood function, okay? So over here, I said, you know, we're going to look at the likelihood after seeing 6 heads and after 10 flips, okay? And then I can take the prior distribution. So if my prior distribution is that that we are centered at r equal to 0.5, my posterior distribution is just going to be the product between the likelihood and the prior, okay? And because these are kind of vectors, I can do element-wise multiplication. And then so here I can plot this, and we can see how observing I did the wrong multiplication here. I need to do prior b, okay? So we can see, I don't know if you, maybe you can't really see. If I do v equal to 0.5, we can see how observing 6 heads out of 10 ever so slightly shifts the distribution of r to slightly favor a value that's above 0.5, okay? And as if I saw 100 more flips, okay, with 70 heads out of 100, then that should shift my posterior some more, and so that would be the likelihood there. And I could plot this, and we can see how it has shifted my my beliefs here. Okay, so we can kind of see there's a little bit of a balance. So the prior was that I had seen kind of 50 heads and 50 tails, and then after I see another 70 heads out of 100 flips, so that's like 70 heads and 30 tails. Basically, my beliefs afterwards is that my coin is now centered at 0.6. Okay, and so perhaps I'll have you guys do this in the homework. We'll look at how different values of the data affect our posterior distribution, which is also affected by our prior distributions. Okay, we'll end there, and we'll talk about other stuff on Wednesday.